Okay, this is part 2 of measuring a mountain, measuring the height of a mountain with a theodolite. And so in part 1 we took a theodolite out to the edge of Sequim, Washington, which is 75 miles away from Mount Baker in Washington. And the mountain is 10,781 feet tall, which is 2.04 miles tall. And we measured 1.076 degrees above eye level. If you haven't seen part 1, you should. I'll link it in the description. And so, first I'm going to show you how we calculate the height of a mountain based on the angle and the distance using full round earth math with atmospheric correction. So, the function we're using is tangent. You can give the function tangent an angle, and it gives you the slope. So, if you give it so many degrees, it gives you a slope, and you multiply that slope times the distance, and then that gives you the height at that distance. So, let's see, fire this up, and recall my... Okay, so here's the whole works. See, can you see the cursor? Yeah, you can see the cursor. Okay, so we take the tangent of 1.076, which is the angle that we measured in the previous video of the angular height of Mount Baker from 75 miles away. Now, we're going to apply atmospheric correction because the atmosphere makes things look a little bit higher than they are over distance, and it's about 1 degree per 932 miles. So here's the 75 miles over the 932, and that gives us a pretty good approximation. I got that off Wikipedia. The formula is much more complex because it takes in like the atmospheric, the pressures and the temperatures and the humidity and all, I don't know what all, and the exact elevation. But for a ballpark for terrestrial things, it's pretty close to 1 degree per 932 miles. So it makes them look that much higher. So I'm taking off, and in fact, we'll come back to that. So right here, you can see this is how high the mountain calculates to be based on this angle, and just with the tangent and the 75 miles, it calculates to be right here. And this is to scale 1 inch per mile. This is not to scale, that's just a straight line. But this is scaled 1 inch per mile. And so this is how we calculate it just on the angle with the tangent and the distance. If we apply atmospheric correction, then this is the number we get, which is very close to the ideal, which is the actual. Anyway, go back to here. So, back to the calculator. So we have, so first we multiply 75 over 932 times 75, so that gives us, much less than a degree. If it was 932 miles, then it would be 1 degree, but it's much less than that. It's 75 over 932, so times 75 miles. So this times 75 is the result. We're taking the result of tangent and multiplying it times 75, and so that will actually give us, so we're taking the angle that it gives us, the angle here, and then we're multiplying, or the slope. We give tangent the angle, and it gives us a slope, and then we multiply that slope with this distance, and then it gives us the rise. So now I'm 150 feet above sea level here. I'm just not that high up. I've walked down to the salt water from here, so it's not bad. So I'm adding in 150 feet's worth, but since we're working in miles, I divide it by 5,280 because that's how many feet are in a mile. So I'm adding in my elevation. Now I'm adding in 8 inches per mile squared, because as I'll show later, if I don't, the numbers are completely off. So I'm adding in 8 inches times the miles squared, 75 miles squared. That gives us the inches of drop on the horizon at 75 miles. So then I'm dividing that times 12 times 5,280. That's 12 inches and 5,280 miles. So that gives us that offset. That correctly calculates the offset in miles. So, and the answer is, look at that, 2.0419. Anyway, very close to what it calculates here. So I'll show you now that 10,781 feet is very, very similar. So 10,781 divided by 5,286. I'm sorry, 5,280. Actually, I wonder what that. Oh well. See, look at the similarities between those numbers. So the official height and using my Theodolite and round earth math, compensating for 8 inches per mile squared, comes out very, very, very close. So round earth math works. Now, let's presume that the earth is flat. The math is simpler because we don't need any of this correction for the curvature. So what we can do, can I still recall that? Yes, I can go in there and I can simply take off the correction for the curvature of the earth. Okay, clear, recall. Okay, now we have the tangent, 1.076, that's our angle. So this is just plain flat geometry. This is, if the earth were flat, this is how you would measure the mountain, the height of the mountain. You take the angle, and again we're compensating for atmospheric bending at the rate of 1 degree for every 932 miles, so 75 over 932. That's the same as saying 75 times 1 over 932. So that we get the tangent of the corrected angle. We take and multiply it times 75, which is the distance here. Then we simply add on our elevation of 150 feet, converting it to miles, and we get 1.33 miles, which is way, way less than 2.04 miles. So you can see if the angle here would be much greater if the earth were flat. We would get actually 1.5 some odd degrees. So if you think maybe just the correction for atmospheric refraction for terrestrial objects is interfering, I will just go delete that. Easy enough to do. Just go in here. Now we're just taking the tangent of the angle, and we're multiplying it times the output of tangent by times the 75 miles, and we're offsetting for our 150 foot elevation, and enter. So now we got 1.4 miles. That's what I wrote down here, but I hadn't corrected for my elevation here. So 1.4 miles. That's still way, way less than the 2 miles that it really is. So, well, maybe we'll take off my compensation for my local elevation, just to see. Okay, enter. Look at that, 1.4 miles. That didn't help, that made it worse. So, there's no flat earth calculation that gets anywhere close to the real 2.04 miles high. So, as you can see, if the earth were flat, the mountain would look this high. This is, I got this nifty handy dandy, oh, well that's too bad. Maybe if I go like this you can see the screen. See, 1.9, 6 miles or inches high. That's how high it really is. It appears to be about this high because it's because of the curvature of the earth. And so you can see, let's see, can you see? Do these line up? Yeah, you can see that I took my little models and I laid them out, and that's how high they show up too. So you can know these are the right size. Almost see it there, but it is very close to see 1.96 almost, and the small one, which represents how it would look with a curved Earth, is again 1.3 something. But I measured those and wrote them down here. So now you might say, well, the theodolite is not accurately reading the width of a degree. It's definitely zeroed out so that level is 0, but do we really know that it's accurately reading the angle that it tips it up? Maybe it's going 1.5 degrees instead of 1 degree or something. So I checked that with these little fake mountains. And so what we got here was, and we don't have to worry about atmospheric refraction because it doesn't happen very much over 75 inches. It's a deal over 75 miles, but it's no big deal at all over 75 inches. So I'm going to go clear here, and I'll show you how I calculate the height of the small model mountain was 1.03 degrees. So we just simply take the tangent of 1.03, and see that gives us a slope. For every 100 units out, it goes 17.97 units up, or whatever. So we can take that times 75 inches, and we get 1.348 inches up. So at 75 inches out, it's 1.348 inches up. So that's the calculated, and the measured was 1.323. Look, that's very, very close. So even at a distance of 75 inches, I was able to measure the height of this with surprising accuracy. And likewise, we'll clear the big model mountain, which was this one, which is the angular size that at 75 inches that Mount Baker should have appeared if the Earth was flat. So we got, for measuring the big model mountain, we got 1.516 degrees. And so we take the tangent of 1.516 degrees times 75 inches. Look at that, 1.895. So 1.89, and this is what I measured it at. So again, very close. So the theodolite is working very well. And I used it with these to prove that the slope was correct, because with a distance of 75 inches and a height of 2 here, or a height of 1.33, whatever it was here, that's a slope, and it doesn't matter if it's 2 inches over 75 inches or 2 miles over 75 inches. The slope's going to be the same. See, watch. Go clear, and we go, let's say we're doing miles here. So it's 2 miles divided by 2 miles up divided by 75 miles out equals, see, there's our slope. Okay, we'll do it. Now we're going to do it in inches. Hey, I had to do this. 2 inches divided by 75 inches equals, look, it's the exact same number. I'm sorry, I had to do that. Okay, don't leave any bad comments just because of that. Pick apart something else. Okay. And that's about it. You can see that the theodolite is correctly measuring the angles for both of these apparent angles, and whether the mountain was at this apparent angle or this apparent angle, the theodolite was working perfectly at both of those ranges, and so there was no option, but it had to be also correctly working at the real Mount Baker. And so you can see that using round earth math, correcting for 8 inches per mile squared, gives you a very, very close reading to what the mountain is known to be, and without correcting for the curvature, it's way off. And you could say, well, the mountain might not be really 10,781 feet. Maybe it's only 7,000 feet. Like, let's say here we go clear. The tangent of 1.076 times 75. Okay, 1.408 miles high times 5,280. So now we've got 7. So you could say, well, it's really only 7,437 feet tall. I'm not buying that, because there's local mountains around Squim here that I've gone hiking in, and one of them is 7,000 feet high, and I've hiked up to the top of it numerous times, and the snow always melts every summer. And if you looked at Mount Baker recently, it's pretty much snowy all the time. I don't think it's ever completely snow-free. It's way higher. So it's got to be more than 7,400 feet. So, but if you doubt me, then I can go ahead and try another experiment where I go 100 miles away. I think I can find a spot where I can see Mount Baker from 100 miles away. And if I can do that, then that would definitely confirm this, because look at what the curvature would be at 100 miles. So, eight inches, actually maybe I should start some parentheses here. 8 inches times 100 miles to the power of 2, that means squared. So you can see that's a lot bigger number. But let's keep going here. So that's the number of inches of drop. 80,000 inches of drop over 100 miles. So I'm going to divide that by... actually, yeah, I'll just... Whoops. Sorry about that. I'll just divide that by 12. So, so that would be almost 6,700 feet of drop, as opposed to only 75 feet of, or 75 miles would be. See, so the drop is almost double just by going another 25 miles. So I haven't gone and done that yet, but I would like to, and that's about all I got to say. There's one more thing I should point out here, and that is just so you understand that the slope is the same regardless of the units, and if you double the distance here, you double the distance here. So I'm gonna shift gears slightly and draw us a line. Look at that, we can go all the way across here. Okay, that's a line. We have a slope. Now I'm going to take and, let's see, this is a 6-inch thing, so I'm going to go at 1 inch. Okay. Pretty close enough. At 3 inches. Yeah, get a little closer than that. Okay. And at 6 inches. Might as well just get all we got. Okay, so this is 1, 3, and 6 inches. Now we measure the height here. It's pretty much 0.494. This is not a really particularly accurate way to measure distance on paper, but, you know, it's quick and it's handy, so that's what we're doing. But it'll illustrate the point here. I really should be using some sort of square device to get it right. Okay, look at that. 1.433. And yeah, whatever. 2.836. So there's obviously a few tens of thousands of error in my measuring here, but you get the point. Look at that, 2.8, 1.4. This is double because it's double the distance. 0.49. So now I bring back in the adding machine. Clear. So if we take and divide 6 or 2.836 by 6, I'll bet you that's the number we get there. So, or very close to it. So 2.86 or 836, 836. That's not a 6. Divided by 6. So we're dividing the height by the distance, or the rise over the run if you want. So divided by 6 equals, look at that, 47. I mean, it's very close. I didn't measure that super accurately. So you can see that with two straight lines that come to a point here and diverge, that if you double the distance here, you double the distance here. It's a simple relationship. So having, 1 inch here and 6 inches here is the same slope as having 1 mile here and 1 mile, So it's all the same. So that's why my experiment of having my little toy mountains down here at inch ratios and comparing it to the mountain up here was perfectly valid, because the height and the distance for the mountain were both in miles, so it's just a ratio, and the height and the distance for the model mountains was all in inches, so again, it's just a ratio. You could have 1 over 1,000, or you could have 10 over 10,000. Oops, that's not 10,000, but it's all the same. It's still 0.1, or no, it's 0.001. Never mind that. But anyway, it's just a slope, and that's why it's so convenient to. Oh, actually, let's see here. I'm just going a little bit more. Look, I gotta be done soon because this is my last sheet. That's why it's so convenient to build a water level and then build a model mountain. And if you make this distance to this distance the same number of inches as is miles to the mountain, so if it's 75 miles to the mountain, then make this 75 inches. And if the mountain is 1 mile high, 2 miles high, whatever, make your little model mountain that high, and then you can sight along the water level. Well, actually, I should have drawn the base of the mountain here, but anyway. And the real mountain way out in the distance. Oh, the distance disappeared. Well, anyway, maybe if I go like. Oh, never mind. So there's the real mountain, whatever. And then you can just sight across the water level, across there, and if the mountain sticks up higher or doesn't stick up higher, then you know that something's up. If the Earth is flat and your model mountain is the exact size in inches that it should be, then it'll sight right across the top of the real mountain. If the Earth is curved, then the real mountain will be down further. So that's what I got.